Okay, so in question 24, it's pretty much a lead on from question 23. And but if you were to do this question independently of question 23, for instance, you could do that. It could be asked independently. We could look at these two pucks. We're told some information about the collisions in experiment 1 and collision in experiment 2, but the question that's being asked is considering the system of the block and the puck. During experiment 2, this kinetic energy system BP increase, decrease, remain the same after the collision. So that's the experiment I'll focus on. So to figure out the kinetic energy, we've got to consider the speeds. The mass needs to be assumed the mass does not change. We're going to consider the speeds before and after the collision. So if we were to do a momentum analysis first to figure out what happened, what is the final speed of block P. So if you look back at question 23, it should be twice, but let's go ahead and prove that. So the delta P of the block puck system is 0. So I should make some room here. So I'll state that the momentum of the puck initial equals the momentum of the puck final plus the momentum of the block final. So if we consider this is the puck has initial momentum P0, has some mass m, and it's moving to the left, and I'll assume it's, so therefore it's moving at some, let's say this is negative m times v. So this is negative big M times v, and the puck final in experiment 2 moves with a positive p0 to the right. So that's moving the same speed. Plus this is the mass. The mass of the block final is mass of the block. Is the same as the mass of the puck. So this is the mass of the B block final. So if I do this, I would have negative mv minus mv is equal to nvbf. And get rid of those m's. So vbf is equal to negative 2v. And that's consistent with the previous question, that in order the momentum of the block needs to be 2p0 to the left in order for the system to have p0 to the left, since the puck is carrying p0 momentum to the right, and they both have the same mass as it's stated here in this part here. So the block must have twice its final speed as the puck. For kinetic energy, we don't have to consider kinetic energy as a scalar. So the initial momentum, the initial kinetic energy of the puck block initial is just the initial energy, kinetic energy of the puck, since the block is initially at rest. So this is 1/2 big M times v, this initial speed, to be squared. Put that inside, you can put that inside parenthesis. But then the kbp final, the puck moves with the same momentum after the collision as it had initially, same collision, so it moves with the same kinetic energy. So this is 1/2 of the mass times v squared, plus we now have to consider the momentum, the kinetic energy of the block afterwards. So we have 1/2 m times 2v all to be squared. It becomes, so this is again 1/2 m v squared of the puck, plus we have this will become 4v squared times 1/2 2mv all to be squared. So we end up with 2.5 mv squared. So we definitely have to increase the kinetic energy of the puck system is definitely larger after the collision than it was initially. Just making sure I do all my math right. So this would be, as stated here, that the block has an unknown device that may activate during the collision. So what a system that this could happen in is that if the block somehow contains possibly a coiled spring where there is some stored spring potential energy, that when the when the puck hits the block, that spring gets released, and that potential energy in the spring gets transferred into the kinetic energy of the puck and the block together, which means, in a sense, we haven't suddenly created any energy in the situation, and the mechanical energy is still conserved, but there has to be some stored, and this device could be something like this, like a coiled spring, to mean that we consider that then a super elastic collision, where the final kinetic energy is larger than the initial kinetic energy.